Hello, my name is Khadija Balakishiyeva from Baku, Azerbaijan. The loss of a hand can be devastating, and the functional limitations following hand loss are catastrophic. Hand amputees start feeling disabled all the time. Even if they are capable of handling it, society will remind them of their limitations, which may lead to suicide. Because of the daily challenges they face, about 1 in every 150 people with disabilities has made a suicide attempt in the past 12 months. In order to overcome these challenges, I found Bionic, which is a brain-controlled device that restores the potential of the anatomy by filling relative assistive technology gaps in the healthcare industry. The Bionic attached to the body via a customized compression cup with sensors that contact the skin. These sensors, electrodes, are placed on the user's bare skin above two pre-selected muscle sites. When a user puts on their bionic arm, flexes muscles in their residual limb just below their elbow, reads data from nerves, surface electrodes translate those contractions to a microprocessor, which triggers tiny battery-powered motors to move the hand by sending them to a control system outside of the body. These vibrations deep in the muscle create an illusion of intuitive and proportional movement that tells the brain when the hand is closing or opening. When your muscles are tensed gently, the bionic hand will move more slowly, and when they are tensed firmly, it will move more quickly. Electrical impulses in the nervous system convey information between brain cells or along the neurons in the nerves that stretch throughout the body. These signals drive the actuators of the body and provide feedback in the form of sensation, limb position, muscle force, and so on. By inserting electrodes directly into muscles or wrapping them around the nerves that control the contraction of the muscles, I send comments to those electrodes that roughly replicate the signals associated with a moving hand, standing up or lifting. The main challenge of other prosthetic devices is lack of temperature sensor. The reason of not putting temperature sensor in most of the prosthetic hands is the assumption of the disabilities don't have to feel the cold or hot as the fact that the arm doesn't belong to them. But lack of temperature sensitivity of the myoelectric prosthetics limits the daily activities of amputated people. Here, where Bionic's innovative side appears, I investigated a non-invasive temperature sensation method. The method I used proposed to train amputees to sense temperature with psychological sensory substitution. I put adjustable fingertip temperature sensors GY906 on the prosthesis to give it a real touch, including pressure, cutting, and temperature. As a result, I had the opportunity to get advanced information about the temperature of the liquid through GY906 at a distance of 2-3 centimeters without touching the water. To level the temperature, I preferred yellow, red, and green colors. There are 3 major techniques I used in the function of an intelligent bionic hand. The first technique is to install a remarkably lifelike prosthesis that has the potential to help the amputated person perform simple daily tasks and to make the healthcare industry more accessible for them. The 8 servo motors are used to drive the bionic hand, where the 5 servo motors S1 to S5 are used to drive the 5 fingers of a bionic hand, and the servo motor S6 is used for the wrist movement of a bionic hand. The microcontroller used here performs the data processing and drives all the servos attached to it. Second technique is to achieve maximum results with a minimum budget. Limb loss presents an interesting paradox. Although it may permit escape from a potential lethal situation, it may result in subsequent cost consequences. Some studies have found the cause of limb loss, others have not. If costs are high, they may dictate against retaining the ability to drop an appendage. I used a large data set derived from the study of a normal prototype to investigate the role of a cost compared with a by-hand prototype. The third technique is to minimize the number of fractures that may occur. Most prosthetic limbs break because they are made of hard materials with small frictions on them, so they cannot bend when they touch a hard surface. To reduce the level of friction between the joints of a hand, it is necessary to avoid small particles. I envisioned the development of by hand using rubber and silicone to make fingers flexible and able to withstand great force. During the ups and downs of the recovery and healing process following your amputation, feelings of frustration and anger are inevitable from time to time. While frustration is a relatively minor discomfort when compared with the intensity of anger or rage, it can still erode your sense of well-being, so it is important to come up with strategies to address it. From the by-hand's design and processes, it can be concluded that the development of a prosthetic hand with real elements of the human sensory-motor system can increase its neural capability, which leads to the movement of the hand. Although it might be a disadvantage to use plastics in by hand as the fact that it can break easily, for environment it is actually an advantage. The by hand's function allows to be produced more eco-friendly prototype in the future. The by hand acts as a durable and comfortable bionic hand that provides better functionality and is more patient-friendly. However, it still has to overcome many obstacles and have significant economic impacts to mimic and improve its hand. I believe that the by hand is a convenient device for disabilities to overcome obstacles that require physical strength in their daily lives. I don't think that disability is different from a person's salary or skills. Therefore, by hand should be suitable for most of them and can make a difference in the use of such project.